Dear friends, in this video we are going to discuss about steam nozzles and its processes in detail. The video will be very useful for all the budding engineers who are working in industries or also doing huge programs. That is, we know about Mach number. If the Mach number is less than 1, we can call it as subsonic speed. At subsonic speed, a decrease in the area increases the speed, velocity, speed of flow. Supersonic flow means Mach number is greater than 1. The effect of area changes are different. So in this diagrammatic explanation, you can easily understand. When the Mach number 1, it is called as subsonic, how the flow is in the nozzle and the diffuser. You can see that. And if the Mach number is greater than 1, that is the supersonic flow in the nozzle and in the diffuser. The nozzle and diffuser are different in shapes. Convergent, divergent, the shape will be different. Significance of Mach number: if the Mach number is 1, the flow is subsonic and the nozzle is convergent. If it is equal to 1, it is called sonic. If it is greater than 1, it is called supersonic and it is divergent. Less than 1 means subsonic, it is convergent. More than 1 means it is supersonic and divergent. Nozzle type: convergent nozzle, convergent divergent nozzle. There are 3 types of nozzles we have: convergent, divergent and convergent divergent nozzle. So the efficiency of the nozzle can be defined as the ratio of useful heat drop to the isotropic heat drop. That is ideal heat drop to the isotropic heat drop, and it is denoted by the letter small k. Not capital uppercase, it is a lowercase small k. That is useful heat drop by isotropic heat drop. Another terminology is critical pressure ratio. It is the ratio between between the flow of velocity to the flow of velocity of the sound in the fluid. So which will accelerate the flow to a velocity equal to the local velocity of sound in the fluid. That is critical pressure ratio. This is the enthalpy entropy diagram. We can look at this pressure P1 and pressure P2. This actual is the dotted line shows this is actual, that is ideal. This is called isotropic. So we are doing only for isotropic problems. We are considering isotropic. When it is specifically given as ideal, we can have this. The curved line is called ideal. That is actual. This is isotropic process. So in molar diagram, we can have more clarity on this. First we can look at the point 1, that is initial condition of the steam, where the saturation meets the initial pressure line P1. Draw the vertical line through the 1 to meet the pressure line P2 at point 2s. This is called isotropic process. H1 H2s is known as isotropic heat drop. The difference between these two is called isotropic heat drop. Yes. Adiabatic. Now if actual heat drop is H1 to H2A. This is called actual heat drop. In the previous slide we have seen isotropic heat drop. Factors affecting the efficiency of the nozzle: material of the nozzle, size and shape of the nozzle, finish of the nozzle, angle of divergence, nature of the fluid and its state, friction, fluid velocity. These are the factors which will affect the efficiency of the nozzle. Selection criteria of the nozzle is: in the first situation, it is used when the back pressure is equal to or more than the critical pressure ratio. It is also used for non-compressible fluids. where we can have the application of convergent nozzles. Cross-section area is decreased continuously from the entrance to exit, that is converging. The area will be reduced, that is called converging. Divergent means area will be increasing, where back pressure is less than the critical pressure ratio, that is a divergent nozzle is used. When we can use the divergent nozzle means critical pressure ratio is less than, that is our back pressure is less than the critical pressure ratio. Third situation is when back pressure is less than critical pressure ratio, convergent divergent nozzle is used. That is, it will have both the combination of convergent then divergent nozzle. Convergent means cross section area is reduced, will be reducing, whereas divergent nozzle means cross area will be increasing. So in the simplified diagram, you can see that saturated stream is expanded adiabatically or isentropically, it becomes wet. In this region, it is wet. 1 to 2 is isotropic expansion. The superated flow is above this dryness fraction line. In the molar diagram, this is called dryness fraction line, x equal to 1. If it is more than x equal to 1, that is superated. If it is less than x equal to 1, that is wet stream. The 1 is superated stream, whereas 2 is wet stream. Yes. The resistance time of steam nozzle is less. That is because of high speed, high velocity of the steam flow. The resistance time in the nozzle is very, very less. So the condensation process will not happen. For that, we are going to have the another concept called metastable flow. That is this Wilson line. This line is called Wilson line. Because of high speed of the steam flow, the resistance time is very much reduced. The condensation is happening above this. This is the saturation line. This is called Wilson line. Next slide, we can see this. That is, the phenomenal condensation does not take place at the expected rate. The condensation delayed for a while. As a result of this delayed in the condensation, equilibrium between the liquid and vapor phase is delayed and the steam continues to expand in dry steam. That is called supersaturation or metastable state. Metastable state. That is, in 0.001 second, the steam to travel from inlet to exit of the nozzle. There may not be any dust particles which generally form nucleus for condensation. At a certain instant, supersaturated steam condenses suddenly to its natural state. This is I told about the Wilson line. There is a limit up to which supersaturated flow is possible. The limit of supersaturation is represented by a curve known as Wilson line on the molar diagram. This line is called Wilson line. This is called Wilson line. Above this curve, the steam is supersaturated. Beyond Wilson line, there is no supersaturation. At the Wilson line, the condensation occurs suddenly and irreversibly at constant enthalpy and then remains in stable condition. The result is to reduce the heat drop slightly during the expansion, causing corresponding reduction in exit velocity, and the final dryness fraction increases slightly. Generally, Wilson line closely follows the dry saturation line, that is, it will be around 0.96. Here it may be the dryness fraction may be 0.96, whereas here the dryness fraction is 0.1. Here it is x equal to 1, here it is 0.96. Mostly the Wilson line will be in this range only. The effect of supersaturation, the condensation does not take place during the supersaturated expansion, so the temperature at which the supersaturation occurs will be less than the saturation temperature corresponding to the pressure. Therefore, the density of supersaturated steam will be more than the equilibrium condition, which gives increase in the mass of the steam discharge. That is the one advantage of effect of supersaturation. And supersaturation increases the dryness fraction of the steam, and entropy is increased, the energy available decreases because of the friction, effect of friction on nozzles. Velocity of flow at the throat get decreased because of the friction in the nozzle. Volume also decreases. Throat area required to discharge the given mass of steam is increased. The terminology: velocity coefficient, actual velocity by isotropic exit velocity, that is C2 dash by C2. So for thank you for watching this video. Thank you all.